Today we study ESA14H, Newton's generalized binomial theorem. We evaluate derivatives of x to the n to all orders. Binomial theorem can be employed to expand this. The change in x to the n due to the infinitesimal shift from x to x plus epsilon, where epsilon is an infinitesimally small, tiny number. The shift can be computed by subtracting x plus epsilon to the nth power by x to the n. Then this effectively, we subtract both sides by x to the n. The leading contribution among these terms is this, whose epsilon dependence appears in the first power. And after that, these terms of order epsilon square, epsilon cube, and so on, until the end, that is epsilon to the nth power. The ratio to epsilon, actually the epsilon, is the shift in the variable x, so the derivative can be computed by evaluating the infinitesimal shift of the function relative to the shift in the argument. And we take the limit as epsilon goes to 0, then I can get the first order derivative of the function x to the n. Alright, when we divide both sides by epsilon, then this epsilon cancels, and order epsilon squared, this means of order, the term of order epsilon square until the end, that is of order epsilon to the nth power. Everything is now divided by epsilon, so this contribution is transformed into order epsilon. Anyway, because epsilon goes to 0, this guy vanishes in the limit as epsilon goes to 0. Because the numerator and denominator, they are both going to 0, we should be careful, but on the right side shows that this ratio reaches a finite value in the limit as epsilon goes to 0. What about the second order differential? So second order differential is this. This is the first order differential. That means if I define this one to be f of x plus epsilon, what we have done was this one divided by epsilon. What is the second order derivative? Now, we'd like to shift this whole object by epsilon and then subtract this one. So, substitute x plus epsilon for the x in here and subtract the identical contribution. Then we find the second order differential as a numerator of the second order derivative. Alright, if I substitute x plus epsilon for x, then this one is replaced with x plus 2 epsilon, and x is replaced with x plus epsilon. Now, this is a carbon copy. We find this is x plus 2 epsilon to the nth power. This one is, they are the same. Minus 2 x plus epsilon. And third one, that is minus minus plus x to the n. So we need to find the simplified version expanded in powers of epsilon. By the way, it is more convenient to express this one in a simple form. We remember this one, x is shifted by epsilon, and then x is replaced with x plus epsilon, something like that. Why don't we translate this the whole object by minus epsilon? Then this expression becomes a very compact form, symmetric form. So this is x, and this one is smaller by epsilon. So this guy is expressed as x minus epsilon, and this guy is greater than x plus epsilon by epsilon. So this one is x plus epsilon. So this expression is a much simpler than this. Eventually, the result is identical to each other. Anyway, we can expand this one to find the binomial expansion of this. Binomial expansion of this can be achieved in a similar manner. And the leading piece, we have x to the nth and nx to the n minus 1 epsilon, and then n minus 1 divided by 2 x n minus 2 epsilon squared, and so on. This guy has negative sign on it. So the order epsilon term in here and there, they cancel exactly. And here we have order epsilon squared term in here, and order epsilon squared term also appears with a negative sign, but that negative sign cancels because epsilon squared. So minus epsilon squared is identical to epsilon squared. So contribution of order epsilon squared in plus term and minus term, they add up. They add up. Therefore, this factor is multiplied by 2 because of the two contributions are the same. And the leading contribution and the previous order epsilon contribution cancel exactly. And then we have remaining pieces that are of order epsilon cube or higher. As a result, I can take the second derivative of x to the n directly from to the x to the n. Therefore, this one divided by this over factor, x to the n minus 2, and divided by epsilon squared, we have additional piece becomes order epsilon, so that becomes a 0. Therefore, second derivative of the x to the n is identical to this. We can make use of systematic ways such as mathematical induction. We can prove that the k-third derivative of x to the n is given like that. We can see we have additional factor that is decreased by 1. And so n minus 1, n minus 2, and so on. And we remember we have a power n minus 2 after the second derivative. After the k-third derivative, we have a power n minus k. And we find this last factor, smallest factor, has a plus 1 relation relative to the final power. So we have final power n minus k, and the smallest factor is n minus k plus 1. Finally, this one, they are the same. Okay, this is what we have found. So this is called the Leibniz rule of derivative of a product function, identical to that one. We evaluate the derivatives of 1 plus x to the non-integral power. That is a rational number. We assume that both the m and n are integers. We assume, first of all, the x magnitude of x, the absolute value of x is relatively small, much smaller than 1 from the beginning. We remember for any integer, and for any integer, the derivative of this is this. Any rational number, a is m over n, something like that, we also have proved that the derivative is something like that. A little bit different point in here is not a function of x, but a function of 1 plus x. There is no big difference. What we have to do is to apply the chain rule, and at the end of the applying the chain rule, we have a trivial factor that is 1. So the derivative rule is more or less the same as this, except that the final stage we have powers of 1 plus x instead of powers of x. Finally, we can apply the derivative by arbitrary order. By the way, in the previous case, because of the factors in the derivative for the integral power function, at the end of the day, we find a factor 0. For example, n minus n, that is identical to 0, and from a certain order on, any high order derivative absolutely vanish. However, if it is not an integer, for example, a half integer, or 1/2, or something like that, 1/3, then there is no way to kill the whole factor, because for any k, it never becomes 0. It never becomes 0. As a result, the kth order derivative never vanishes. The kth order derivative never vanishes. So derivative survives to arbitrary power, to infinity and beyond. It is a striking difference between the case of integral power that is called polynomial. Finally, we can find this power series expansion just like what we have done with when we approximate the square root of 2 or square root of 3 or something like that. We assume that first of all, when I substitute x equals to 0, 1 to the arbitrary power is just 1. Therefore, we expect that if the absolute value of x is tiny, it must approach 1 as x goes to 0. We assume that this left-hand side can be expressed as a sum of powers of x, because the simple reason is that we know the integral powers are very simple to deal with. That is called a polynomial. As far as the error analysis is concerned, integral powers are very strict, that their errors will decrease as the powers decreases, unless the overfactor do not have a strikingly large growing factor. Okay, why don't we take the derivative, kth order derivative? Even though the left-hand side, we know the general rule for the derivative for the left-hand side that can be obtained like that. Right-hand side, the kth order derivative is trivial, except that we know that left-hand side has arbitrary powers of derivative, so we assume that the right side, this series, does not terminate at a finite value of power. Finally, I can take the derivative on the left-hand side with this formula and then substitute 0 for x. And right-hand side, the kth order derivative is very simple. After taking the kth order derivative, I have ck, and ck x to the k, kth order derivative will give k factorial ck, and then the remaining piece has x squared x higher order pieces. If I substitute 0 for x, everything else will vanish. Exactly. So, this is a very strong constraint from which we can determine the coefficients of any integral power. The polynomial's coefficients are completely determined to any order. But as we know, because this power is not an integer, this series does not terminate. Finally, we have found this ck is like that. We are familiar with the fact because the kth order derivative of x plus 1 to m over nth power is given like that. As a result, we can say this series has the same derivative to any order at x equals 0. Substituting 1/2 for that non-integral power, fractional power, we can find coefficient is like that. And if I substitute this one, this square root 1 plus x can be expressed as a power series of x. And we have a strange notation that is called a factorial factorial. That means 4, 2, 6, 8. It is 4, 3, 2, 1. We say it is 4 factorial, right? This factor decreases by 2 instead of 1. In a factorial case, we say it is 8 factorial factorial. The 7, 5, 3, 1. We say it is 7 factorial factorial. We have a special value. 0 factorial is a non-zero. We define this one to be 1. In a similar manner, if I define the factorial factorial, then for the even case, the odd case, we have minus 1 factorial factorial is not minus 1 but 1, and minus 3 factorial factorial is a minus 1. With this convention, we can make use of these factors that can be determined by comparing the derivatives, kth order derivatives of both sides. We can re-express the square root function as a power series of polynomial. That's it for today. Thank you.